Okay, let's start our monthly discussion of the near-field cosmology. Okay, today we have two speakers. The first one is Benjamin Wiggers, and the second one is Jiske Starkenberg. And the first title is about the testing hierarchical structures formation around dwarf galaxies, predictions for LSST. Yeah, I think he want to um, do something about the lambda CDM and to test or something else. And the second one is a statistical populations of the state streams and shares around of galaxies for LSST and friends, and which will be given by the second speaker, Jiske. And Jiske Stackenberger is from the Northwestern University, and Benjamin Wiggers is a PhD student from Damos College. Okay, let's welcome the first speaker. Okay, Benjamin, here we go. Okay.
Okay. Excuse me. Sorry. Y'all can hear me. The screen sharing is on and everything.
Yes.
Okay. Perfect. Thank you. I really appreciate the opportunity to talk to you all today. Not sure what time zone everyone's in, but it sounds like we got people from kind of all over the place. So thanks for making it, whatever time it may be. My name is Ben. I'm a first year PhD student at Dartmouth College. I work with Professor Burchin Mutlu-Pakdil, and we just started this project trying to test and understand hierarchical structure formation around dwarf galaxies in the near universe and make some predictions for what LSST will see in lambda CDM. So let's get started. Oh, it's playing, thank God. So hierarchical structure formation, everyone in this call, I think, knows what this is. This is the near field cosmology group. But for the sake of completeness, galaxies grow in a bunch of different ways. One of those ways is through accreting their own satellites. This is a GIF that folks I'm sure have seen from the Auriga simulations of a Milky Way-like galaxy um, with some satellite population, some of which are getting disrupted in the streams, some of which are phase mixing into this sort of puffy, diffuse stellar halo. And all of this is remnants of galaxy mergers, either in the future or in the past. And mergers like these are expected to occur at every mass. Dwarf galaxies are expected to accrete even smaller galaxies. But studies of those sorts of accretion events are much harder to study than the ones in the Milky Way like galaxies because they're so much fainter and so much smaller. But recently, some folks with the Delve Deep team and the MadCache team have found evidence of these galaxy mergers around LMC and SMC-mass dwarfs. There's some streams and shells and satellites being disrupted. And LSST is going to give very similar data to these two surveys, and it covers a larger area of the sky. It observes many more of these galaxies, and so we can start to do some sort of statistical science and understanding of the stellar halos of dwarfs. But to do that, we need predictions first. We need to understand what our best guess of cosmology tells us about the hierarchical formation of these dwarf galaxies so we can interpret observations from LSST and similar surveys in the cosmological context. And that's our goal. Just make some predictions for what LSST will see. And to do this, we use some of the Marvel-ous Dwarfs, the Marvel-ous cosmological simulations. We select roughly 20, maybe a few more LMC or SMC-mass galaxies from these simulations. We make mock observations with resolved stars, inject them into a background using the LSST photometric system to try and understand what we're going to see, make some predictions. So this is a GIF of one of the dwarfs that we observed. This is an SMC-mass host, and is going to be the one that I kind of use as an example throughout the methodological part of this talk. You can see it experiences quite a few mergers throughout its life, and then a big satellite comes in and disrupts it, creates this giant stream that's really pretty. And we're going to try and understand if LSST can see streams like this one. So first, to go from a simulation to a set of resolved stars, we use this package called PyAnanke. Have folks heard of this? This is, okay, good. Developed by Adrian Thab. He's been great. He's helped me a lot to try and understand how it works. But basically, it takes in all the information about these simulated star particles, positions, kinematics, various chemical abundances, masses, ages, everything. It assumes each particle corresponds to some single star formation region or localized period of star formation. draws individual stars from your IMF of choice. We use a Krupa IMF here, distributes them in space according to the local density of star particles, assigns magnitudes based on your photometric system, and the masses, ages, and metallicities of all the different particles, shifts the stars to a distance that you want, and cuts off the catalog at some lower limit in magnitude. So in terms of distances and depths, the two we care about are 2 megaparsecs, 4 megaparsecs, the year 1 depth for LSST, and the year 10 depth for LSST. Those sort of bookend the best case scenario being the closest and deepest observations, and the worst case scenario, which is the furthest and shallowest observations, to give us this sort of wide range of understandings of what LSST will see in various galaxies at these different times. And then with these in hand, we have to throw them into some sort of background that we generate. We just take some past observations that my advisor has done of an empty field in a galaxy from, I think it's NGC 253, taken with DCAM. Since that field is pretty small, we have to scale it up to fit, again, the simulated dwarfs inside of it. But we have to make it look realistic. So we keep the surface density the same on the sky. We fix the density as a function of color and magnitude, and we randomly draw points to populate a CMD in a realistic way, holding those things consistent. And then we just kind of stick the dwarf in there. On the left, this is the same dwarf galaxy that I showed the GIF of. It's got the nice stream going around it. But when you stick it in the background, a lot of that goes away. We see the dwarf, we see some clumps, we see a hint of a stream, but just by eye, it's not quite so obvious that all of this substructure is here. And so to pick that substructure out, we use the matched filter detection algorithm. It's basically a signal processing technique that you can use to maximize your signal to noise. If you have some expectation of what your signal is, for us, it's an old metal poor stellar population. And when you have well-defined noise, which is the background catalog we just generated, you can sort of assign weights to each particle or each source, be it background or simulated star particle, and then bin those across the sky. And then each bin on the sky gets sort of an average weight of each particle that's within it. And then we can draw some contours and confidence intervals around those points. And you can see that map on the right is that same galaxy from before, but the stream pops out way better. That's kind of all the technical stuff, the methodological things. Do folks have questions before I show some early results? Going once, going twice. Okay, so same stream. This is with the year 1 depth at 2 megaparsecs, kind of zooming in a little bit. We detect the dwarf and we detect some of the stream. That's great news. The first data release of LSST will see some kind of substructure around these things in Lambda CDM. But you don't see all of it, just this sort of upper quadrant. It's not extremely significant. It's almost at the level of the background. But something I do want to emphasize is that with this match filter technique, there are a lot of knobs to turn. You can pick a different signal. You can bin that signal differently. You can bin your noise differently. You can bin things on the sky differently. There are a lot of choices that can be made to make these different things pop out. I've been working on this for 3 months. This is my best attempt right now. Things will change. This may get better. But it's important as observers and as people making mock observations to understand that we can inform our choices based on what the simulated galaxy kind of looks like. And that makes the choices on the real dwarfs much better. So even though it doesn't look great now for this year 1 depth, this is a first attempt. There are so many more options that we can try and so many different ways that we can make these maps that it may look better. But regardless of choices, in year 10, look how great that is. Look how much that stream pops out. You even get a little hint of this spur on the side, maybe a little bit of this puffiness. Comes all the way around. You can see sort of a density profile. And this is a great tracer of the underlying dark matter halo. This is a great tracer of the murder history of this galaxy. This I just think is amazing. I really love this image. You may notice that this little clump right here doesn't show up in either of our maps. That's because this color bar is by age. Those guys are a little bit younger than the rest. Right now we're selecting for the yellow guys, the really old metal poor ones. if we made a different choice in what our signal would look like, we could make this little clump, small satellite pop out. That's not what we're going for with this. Again, just to emphasize the choices matter in this match filter detection. Um, that was one with a nice big stream, but we also have dwarfs that have satellites around them. Again, this is 2 megaparsecs, year one depth, also an SMC-mass host. Looking at these old metal pore stellar populations, you see a little hint of this sort of tail stream here, but primarily you get this clump right here, which is a satellite that is 10 to the 7 solar masses. And this is at the year one depth. We don't see these two little guys. I zoomed in on the plot because there's just all noise out there. But at the year 10 depth, you do pick out those two little guys. And those are both about 10 to the 6 solar masses each. So with an extra magnitude of depth or an extra 10 years of survey time, you get an extra order of magnitude in the satellites that you can pick up around these SMC mass galaxies, which I find really interesting. I think that's really cool. So again, very quick, that's kind of all I have to say. Uh, Summary I'll leave up, but future work, I've only shown 2 galaxies of the 20 odd that I have. So there's plenty more hosts to analyze. There's a lot more work coming through the pipeline. And with this full set of mock observations being 2 distances and 2 depths for all 20 galaxies, various signals and ages and stuff for the match filter detections, we can quantify pretty strongly a lot of constraints on how well we'll be able to detect these streams and shells and satellites, and what that means for Lambda CDM, and be able to have a really solid basis of comparison when LSST comes out. So thank you very much for listening. I'll be happy to take any questions, but also pieces of advice that you guys, or not advice, pieces of analysis you may want to see in the future. I'm kind of at the point in this project where I can add in new things. So if there's stuff you guys think would be cool to see, please let me know. Thank you very much.
Thank you, Raj. Any questions?
I actually had a question. So this was a great talk, Ben. I was kind of wondering, and you might have said this, but like at what distance are you going out to with these like mock observations? Like when you showed the year one, year 10 depth comparison, like how far away are those guys again? Oh, it was 2
So
megaparsecs.
these ones
Okay.
that I'm showing is 2 megaparsecs. We pick 2
Okay.
and 4 because 4 is kind of the limit that we'll see resolved stars at with any level of completeness. And 2
Mm,
is kind of the closest LMC slash SMC mass satellite that isn't the LMC and SMC themselves in LSST's footprint. So again, just kind of bookending the range of things that we'll see closest and
mm,
furthest.
nice. Have you thought about doing anything with like maybe like diffuse light and something similar to this, like looking for like how that structure shows up, or is that not
Mm-hmm.
of interest really?
So this is kind of a two-pronged project when it was given to me. I think the resolve star stuff is more interesting, but we definitely are thinking about the diffuse light because the surface brightness depths, you can go a little bit fainter and a little bit further. Um, but I think the resolve stars are cool because you can like pick out individual masses and metallicities and things and do a lot of learning about progenitor systems in the merger history, which I think is really cool. But yeah, that's for sure something that'll be happening maybe in the next year or two.
Sweet. Thank you so much.
I have a curiosity. Probably you already mentioned, but sorry, I was stuck with some institutional email. Um, from the simulation, do we have an expected mass distribution for the dwarf around for the satellites of dwarf galaxy? And is this any case, is this distribution matching what you observe?
Sure. So we do have an expectation. I should say that I've never worked with simulations before 3 months ago. So questions about the simulations themselves, I don't think I'll be able to answer super well. There is an expectation of the distribution for sure. And we will be able to see above some mass. Um, so in the sense that these are mock observations, the detections above some mass limit is going to match the distribution that the simulation has. Whether or not LSST matches that distribution is yet to be seen, and that's kind of what we're trying to make predictions about. Does that answer your question?
Yeah.
Okay,
Thank you.
sure.
Go ahead for our other questions. Yeah.
Yeah. Oh, I have a question. I actually have multiple questions, if that's okay. But
Sure.
they're connected. So I was wondering for the last figure you showed, where you have the smaller dwarfs that you can just pick out in the 10-year data, what's the signal to noise level on those roughly?
So
Like how confident are you?
Yeah, so the outer contours is 4 sigma, and then it goes like 4, 6, 8, 10,
Okay.
20. So these little pockets of noise are a single contour, and these
Okay.
dwarfs have 2 or more. So if I chose to visualize just like 5 sigma and up, these would appear, these guys would go away.
Yeah.
If this was a real observation, it would be really hard to tell precisely if those are real or not. Since I know that they're there already, we can say that
Yeah.
they're detected. But whether or not we can make that claim in actual data is a different thing.
Yeah, that's where the next part of my question was going to. It's like, would you have sufficient different dwarfs around dwarfs from the simulations that you can get a sense of where what the completeness would be at, like right at that limit?
Yeah. I think we have enough that have a various satellite populations that we can make some kind of claim about it. Another thing to
Okay.
keep in mind is that we can't really do star galaxy separation in our mock catalogs in the same way that you would with an actual catalog. So this is kind of like a worst case scenario. We're fully complete, but we're really contaminated. And if you look at something like Delve or like Mavcache, where they have the shape of like semi-resolved background sources, and you can remove a whole lot of that contamination really well, while still remaining fairly complete, those things will pop out much better. And that's something that you'll be able to do in LSST as well. So we're trying to make some educated guesses and do our best job, but it is also true that with star galaxy separation, like the DES year 6 gold thing, not exactly sure, this will get better.
Okay, great. Thank you.
Any others? Actually, I have one question. We all know the LMC Magellan clouds and the LMC or SMC is very gas-rich systems. How do you consider this effect in your cosmological zooming simulations? Yeah.
We're only looking at star particles here. That's an interesting thing to look at in the future. I'm not sure how the simulations handle it. I don't work directly with the simulations themselves. That's something I could ask a collaborator.
In general, isolated dwarf galaxies and simulations are gas rich.
Sure. Okay. I know there are gas particles there, but that's not something that I use as part of my mock observations.
Yeah.
Exactly.
Cool. Okay. Any others? If no more, we shift to the next one. Please, Jiski. Stackenberg. Yeah. I think we can do the next one. Yeah.
Okay.
Thanks again.
Yeah, cool. Thanks.
Okay. You can see my slides?
Yeah. Yes.
Okay. Thank you. So thank you for having me today. And this is actually, it's great to be able to follow up Benjamin, because I think it's a different view on some of similar questions. And this actually fits in very well with what I'd like to show you today. So I'd like to talk a little bit more about how we can get statistical population predictions, mostly focusing on streams and shells around dwarf galaxies for LSST, but also for other upcoming and current surveys. And actually, I have to say that at the end, I've added in a few slides on other projects that are led by junior people I work with that I think could also be interesting to you. And so I'll very briefly mention those two, so you can ask more questions about those as well. Okay, so again, similarly in the broader picture, stellar halo satellites and tidal debris provide a wealth of information. We can learn about a galaxy's past evolution and more about how low-mass galaxy formation works. Most of the information that we have about low-mass galaxies comes from satellites, in that case of the Milky Way, because we can study them in detail. And the extended streams and shells, but also globular clusters and satellites around systems provide us with information about the host halo potential, potentially constraining dark matter, the nature of dark matter and the halo properties. So we've seen a lot of substructure in the local volume around other galaxies, and this has been a very rich data set, but most of these are more massive systems. And so with, and actually there's one found in LSST, as has been shared on the Slack. But with deeper and larger surveys, we're starting to find more and more features around dwarf galaxies. And I wanted to highlight this work that's expected to come out in the coming month from Joanna Sakowska, who has been looking at structures around dwarf galaxies. So please keep an eye out for that. Of course, with both Euclid and LSST and Roman, this space of low surface brightness, and especially for lower mass galaxies, is a huge discovery space. And so I'm very excited that of all the data coming in and the data that will be coming in the next years. On the theory side, I wanted to spend a little bit of time talking about the different ways that we can make predictions for these galaxy stellar halos. And there's a conflict here because we cannot simulate the full history, full galaxy formation for a large number of galaxies at the resolution where you can study the detailed evolution of dwarf galaxies falling in, how they form streams, and how they get phase mix into the stellar halo, let alone simulating, for example, globular cluster formation and evolution within a larger galaxy or even within a larger population of galaxies. So there's this whole range of different theoretical methods that gives us some pieces of the puzzle. And my main message today would be that we can learn from all of these, and we should be learning from all of these and combining the information that we get from different ways of looking at this problem and looking at predictions, and compare them all to observations as well. So on the one hand, we have the large box hydrodynamic cosmological simulations that have large numbers of galaxies, and they have the full galaxy formation physics up to a resolution, limited resolution, but they have limited resolution. And they might not be able to resolve dwarfs of dwarfs or satellites of dwarf galaxies. On the other side, we have hydrodynamic zoom-in simulations that put in as much of the galaxy formation physics as they can. They have higher resolution, but they can do only very few galaxies. And in this case, you could focus completely on the evolution of a dwarf galaxy and look at its satellites. We can populate this whole space in between with different ways to try to combine methods, like do particle tagging based on embodied cosmological simulations, do semi-analytic galaxy evolution models that are based on the merger histories within larger simulations, but then do the galaxy formation physics separately, and therefore they don't have spatial resolution, but they can go to higher mass resolution. And on the other hand, we have isolated halos, which are or isolated simulations, which are dynamical modeling in restricted embody or evolving basis function expansion models, where you have either a life potential or you model how the potential evolves, and you add in basically test particles or tracer particles that would be your stellar structures. And we also have dynamical model in static halos, which actually has been the one that's up to now has been mostly used to study, for example, stream formation from globular clusters, because you can run many, many models, and so you can actually try to mimic effects of observations and try to match them. So I'm going to talk today about semi-analytic galaxy evolution models, and especially building on top of this to model how satellites evolve into tidal features around dwarf galaxies. And so how we do this, we actually use the output of a galaxy formation semi-analytic model, which in this case is the Santa Cruz semi-analytic model, which tells us the evolutionary history of an LMC-sized halo, which is what we're looking at, the evolution of the main halo, and all the properties of the dwarf galaxies, or the satellites that fall in, when they fall in. We can sample orbits from cosmological simulations and make sure to sample the distribution well. And so then we know when a satellite falls in, what its orbit is. We can do detailed orbit evolution and model the stripping of the dark matter halo using the semi-analytic model called SatGen. And then what we do additionally is actually estimate the evolution of the orbits while the halo, its parent halo, is growing and is evolving. And then predict what the lifetime of the tidal debris would be. How long does the stream survive? How long is it? How wide is it? What are its properties or for a shell? And use that to predict surface brightnesses and stellar densities. And so, because this is also analytically, we can basically do this for arbitrary many halos and get a statistical estimate of how many streams and shells and phase mix structure you expect around LMC-sized galaxies. Okay, so this is it doesn't look like it. It's actually a complicated plot because objects fall in as satellites. They can survive for a while, then they can start forming streams or shells. Streams can actually evolve into shells, and then later on things are phase mixed. So over time, this plot shows roughly how many streams, shells, how many objects are phase mixed, and how many surviving satellites there are around an average LMC. But in its evolution, things in these categories move into each other, which is part of the evolution in the curves. And so we can use this setup to generate accretion histories for very large samples of isolated halos, predict the evolving substructure, and then use this arbitrary large sample size to provide robust predictions and for observations. Basically, our key finding is that LMC-sized galaxies should have tidal features. And then the next question is whether they're observable. What I wanted to point out is another benefit of using the semi-analytic model is that you can change the underlying physics and rerun, and so explore the space of changing physical parameters and see what the effect is on the predictions. So specifically for LSST, these are my preliminary predictions for how many streams or how many features, streams or shells, you would expect around an LMC-sized galaxy And so what I'm actually plotting is for surface brightness, what the fraction of LMC-sized galaxies is that would expect 1, 2, or more tidal features. And so you can see that you start to expect seeing a tidal feature around some fraction of the LMCs around our many current limits, which is around 28. And we've seen a few in observations. But when you go deeper and you get close to like the 10-year limit of LSST, you expect to see tidal features around 50% of the LMCs in this model. And actually you expect to see multiple features around some of them. We can also forward model this for other surveys, for example, for Euclid, in this case for the visual. I show it for the visual band, as well as for the Roman wide field survey, where I show it for the H band in this case. And you see that because of the color difference and because of the depth difference, these numbers are probably slightly different. But many nearby galaxies, especially at the LMC size, will have visible tidal features. There are other challenges to actually detect these, which is what Ben also showed. And the other thing I wanted to ask, because we can change the physics, the underlying physics of galaxy formations, in this case, I can, for example, test what happens if you make the stellar mass-halo mass relation at the low mass end much steeper. If we have a much steeper stellar halo mass relation at the low mass end, then the number of features that you expect is much, much lower. And I can go back and forth. And so changing the physical assumptions can change the predictions. And so we can use this format to actually get a constraint from statistics we will see in these observational data sets. And in this case, I have to say the change I made to the stellar halo mass relation is pretty extreme. It's like this version is ruled out already, but to show you the effect it can have. Okay, so this is all what I wanted to say about the semi-analytic model. I would really like to say a little bit about another way we've been looking at stream formation, and in that case, stream formation from globular clusters, which is within evolving dark matter halos and zoom simulations. And so looking at tidal features at external galaxies, we need to realize that these galaxies form differently. They have different evolutionary histories than our own Milky Way. And so one question that we wanted to study is how mergers affect the stream properties, and do streams survive mergers? So we set up a simulation to test this and study how these streams are affected by large changes in the potential that they live in. And I will only show you this movie. And we have movies of all the individual streams and what their evolution is, and you can find them at this website at the bottom, and also at the QR code, the linked QR code. And so you see the satellites coming in the background potential, and what you see is that all streams react to the satellite, but in very, very different ways. Some get dragged completely out. Some actually go farther in. Some go from radial orbits to more circular orbits. Others go from more circular orbits to more radial orbits. And so the full population of stellar streams changes a lot. But most of them seem to survive in some way or another. Okay, and we dubbed this the dancing streams in merging halos. So the other project that I wanted to highlight is a collaboration in which we're working to do realistic globular cluster stream formation in a cosmological context. And so in this case, we start from hydrodynamic zoom-in simulations. We use a cluster formation model on top of that to identify the places where star clusters would form. We evolve the star clusters in isolation, but with the tidal field of the evolving galaxy they live in, with a cluster evolution model. That gives us the evolved clusters within the larger galaxies, so we know exactly where they are and what their properties are. And then stars that are ejected from the cluster, we put back into the evolving potential of its parent halo to study how detailed stellar streams form. And so in this context, we have star by star stellar streams from a realistic globular cluster model within its parent halo as it is cosmological evolving. And this is one example of the streams that we got out, one of the first that we looked at and that we present in this paper, a recent paper. In this case, the stream actually has a clump on one side, which seems to be from an interaction with the disk of the galaxy, the host galaxy. And I also wanted to highlight a work by an undergrad student who this summer has taken these star-by-star stellar streams and moved them to an M31 distance with an M31-like stellar halo, as well as a Milky Way foreground, to see what these would look like, in this case, for Roman observations. But in addition to having a star-by-star stellar stream, we also have binary stars in streams. We have compact objects in streams. And so there's a wealth of data that we are trying to analyze. And we don't just have one stream. We actually have a large sample of globular clusters that evolved in this parent galaxy and that all are forming streams. And so, yeah, we hope to show more of this in the coming months as well. Okay, and then I would like to end with this full picture of how people are trying to make theoretical predictions and theoretical understanding of galaxy stellar halos and the structures that evolve within them. And thank you so much for your time.
Thank you very much. Questions? Comments?
Hello, I have a question. Very interesting talk. Thank you. I have a question about the first part of your talk. Could you please go back to the plot of the number of galaxies per number of LMC objects?
This one?
This one.
Okay.
Yeah. This is very interesting because if I correctly understand this plot, the satellites forming shells, basically they form shells at the beginning in very early eras. This means that we should not see new objects forming shells in more recent times. And since it is under discussion if, for example, Fornax dwarf spheroidal as a shell or not, I was wondering if, okay, this is a plot, a study, a simulation for LMC galaxies, but this, in your opinion, holds also for Milky Way size galaxies?
I think shell formation, well, there are two things that play a role there. Actually, the first thing I would say is, yes, you see most of the shell formation at early times. Reasons for that is that most of the mergers happen at early times. And especially the higher mass ratio mergers happen at early times. And so that's why you have more shell formation there. And the streams pick up later. However, the part of this project that I'm still working on is the observability of shells and how long I have a sense of how long streams survive, but I'm still working on how long shells survive. And so even though you might have less shell formation at late times, I think there's actually a likelihood they stay visible for a longer time.
So basically,
And
this
so,
means that this plot should be seen as an upper limit.
yes, I think so. Yes,
Yeah.
but you could see this is formation, so you could see a cumulative effect there, possibly. And another effect is that when streams evolve in time, they can actually form shells themselves. It's like part of the stream can transform into a shell, and I'm trying to capture that. But because the halo is also evolving, that's actually a complicated part of this. So I don't feel confident in saying anything about this is the absolute maximum of shells.
All right.
Yeah.
All right.
So
Thanks.
I'm sorry about that.
No. It's very, very
It's a work in progress.
Thanks a lot.
Yes. For the question about Milky Way, so Milky Way sized halos on, I think the key thing there is that it's if you have a similar spectrum of infall masses, you would expect a similar number of shells, except that the stellar masses of those objects are higher. And so you're much more likely to see shells.
Okay.
Like any satellite that falls into an LMC could have an extreme low stellar mass to halo mass fraction. And so even though it dynamically will form a shell, you might not see that in the stellar distribution in the stars. There might be very low stellar mass to actually give you a visible shell.
All right.
For a same mass ratio merger for a Milky Way, the satellite will be more massive in stellar mass. And so you would actually see a shell.
All right. Thanks a lot.
So, no, it's a good question. Thank you.
Thank you.
Any others? Oh, for your group clusters part, I'm just curious. Could we define some tidal radius or some half-light radius of these streams or group clusters?
Oh, so for the globular clusters themselves, we have the full tidal field and their internal mass profile.
Mm.
So we know exactly where the tidal radius is.
Yeah.
And then because we know the potential of the globular clusters, we can actually, when we add the stream particles back into the zoom-in simulation, we can also add the cluster potential itself.
Okay.
And have it evolve properly in time as well.
Okay, thank you.
Okay. Thank you so much.
Okay, do we have some? If we don't have any other questions, I stop this recording.